Good morning, everyone. My name is Jonathan Buck. I'm an engineer here at ATA Engineering, and I'll be your host for our webinar this morning. My clock has 10:01, so I'm going to go ahead and get the ball rolling here. The topic of today's webinar is an introduction to NX CAE tips and tricks. Before I dive into the webinar, I'd like to take a step back and tell you a little bit about ATA Engineering for those of you who might not be familiar with us. We specialize in providing test and analysis-driven design solutions for the most challenging mechanical and aerospace engineering problems. We have over 30 years of experience using Nastran as well as many other solvers on a wide variety of problems ranging from structural dynamics to computational fluid dynamics. We're also a value-added reseller of Siemens PLM Software's CAD, CAE, and PLM software packages. If this is of interest to you or you'd like more information, we invite you to visit our website dedicated to your PLM software needs. Okay, having said that, let me tell you where we're going this morning. I'd like to start just by outlining some introductory concepts in NX CAE so that we all have the same working knowledge. And then from there, I'll move into some demonstrations. We'll look at a static analysis of an electronics housing. I know we promised a bike crank in the advertisement for this webinar, but we made a last-minute change. But rest assured, you'll still see all the same content. And in this demonstration, we'll see the process of analyzing a component, as well as the process of updating the design, reanalyzing it, and comparing it against the baseline design. And through this process, we'll see the power of a tightly integrated CAE tool like NX CAE with NX Nastran. And then the next set of demonstrations we'll look at will highlight some short tips and tricks that we've picked up through years of experience that we think might be of interest to you. In particular, we'll look at mesh morphing, we'll look at the solver export options, and we'll look at post-processing templates. So like I said, I'd like to start just by describing from a high level some introductory concepts in NX CAE. And the first thing I'd like to point out is that NX Advanced Simulation has a distributed file structure. So if you look at this image you see in the slide, at the top left you see a standard part file. Now I'm sure almost all of you are familiar with these part files. These are the standard CAD files that we operate with when we're doing modeling and design. But when we're in the realm of CAE, we have several other files to contend with. The first is the Idealized part, then we have the FEM file, and then above that we have a SIM file. Now let's look at these one by one. And let's start by talking about the Idealized part. When you think about this Idealized part, I want you to keep two things in your mind: idealize and augment. When I say idealize, what I mean is that you can do certain things to the geometry, such as remove holes, remove fillets, remove chamfers, things of those nature, defeaturing the geometry. And when I say augment, I'm talking about adding to the geometry in some way or modifying features such as splitting a body or a volume, subdividing surfaces, or creating entirely new geometry for the purposes of analysis, configurations, or trade studies. Now from a high level, the reason we do these operations in the Idealized part is because it's often convenient from an analysis perspective to do these kinds of operations on a solid body, clean up the geometry, make minor tweaks here and there for the sake of getting a nice high-quality mesh on the body. But in doing so, we don't want to corrupt the underlying design geometry because it's the part file that really conveys the design intent that the modeler had in mind when he or she created the part file. And as analysts, we don't want to disturb any of that design intent, and we want to be able to perform our finite element analyses in such a way that another modeler or one of our colleagues can open up the part file or open up an assembly that references the part file and see the part as the designer intended without having to contend with these things that we do on the analysis side in the way of model cleanup, geometry abstraction, or geometry idealization. Now the other thing I want to point out here is that the way the idealized part facilitates this kind of hierarchy is by creating an associative copy of the design geometry. Now, as a consequence, what this means is when you're working with the idealized part, you have to enable revisions to that body through the promote command. And what this does is it makes the associativity one-sided, which is to say changes to the underlying part file propagate up to the idealized part, or in other words, changes to the part file can be seen in the idealized part, but it's not a two-way street. Changes to the idealized part do not affect the original part. And again, that is to preserve the underlying integrity of the part file and prevent the analyst from corrupting the design intent of the part file. Now let's look at some of these other files. We talked about the idealized part. The next part in the next file in the hierarchy is the FEM file. And as the name suggests, this is where your finite element model resides. So your nodes and elements, physical properties, and material properties are all created and stored within this file. Now typically this file also includes a reference to the geometry that comes from the idealized part file. The file above that is the sim file, or the simulation file. And as the name suggests, this is the file where you actually create simulation objects, define analyses, put together loads and constraints to form boundary condition sets, and specify the type of solution sequence or the type of analysis of interest, whether it's a static or dynamic or what have you. Now there's a fourth file type as well that wasn't in that image we saw just a short while ago, and this is the assembly FEM file. Now at first glance this is a little bit hard to wrap your head around, but I want to encourage you to think of this as the finite element analog of a CAD assembly. So if you think about how we operate with assemblies, when we have repeated parts, what we do is we have a single part file to represent, say, a fastener, and then we just make copies of that part file and instantiate it in the assembly any place we need it. We don't create unique files for each and every instantiation of an identical part. So assembly FEMs work in much the same way. If we have a body or a component that appears in multiple places throughout an assembly, we can mesh that body once and then reuse that mesh in the context of an assembly FEM and save ourselves a lot of time and effort by just having to mesh a body one time and then being able to reuse it throughout the assembly. Now we can look at this in a bit of a graphical way, which certainly helps me, and I like to visualize it as a tree, as you see in the bottom of this slide. So if we start at the top of the tree, we have a part file. A part file can point to any number of idealized part files, which in turn can point to any number of FEM files, which in turn can point to any number of SIM files. Now the other reason it's helpful to visualize the file hierarchy as a tree structure like this is because it also gives you some insight into how the file save as operation performs. And in a nutshell, what happens when you perform the file save as operation is that the files at any level of the tree and any branches below it are saved. So to give you a concrete example, suppose we were working within the context of this sim file down here. If I were to click File Save As, the only file that would be saved is this sim file. If I were working within the context of this FEM file, however, as soon as I do a File Save As, I'll have the opportunity to save the FEM file and any of the sim files that reference this FEM file. And so by analogy then, if I were at the very top of this tree and performed a File Save As operation on this part file, I'd be able to save the part file, all of these idealized part files, the FEMs, and the SIMs. Now the reason this is important to understand is because oftentimes as analysts we like to perform trade studies or what-if studies, and we like to change the size of a hole or add a boss here or increase a fillet radius there. And for doing these kinds of one-off trade studies, File Save As operation is a very handy way to create branches in this file hierarchy and rapidly iterate on your design studies. Okay, having said all that, I'm going to dive into our first demonstration here. And for this demo, we're going to look at a static analysis of an enclosure for a piece of electronics hardware. So what we're looking at here is actually half of the enclosure. And what we want to do is we want to analyze the stresses right in the vicinity of these bosses due to the load created by the snap fit process of the mating half of this enclosure. So the first thing I do is I switch to the NX Advanced Simulation module. And then once I'm here, I click this button at the top left to create a new FEM and simulation. And up comes this dialog box, and by default, it's set to NX Nastran, which is what we'll use through the course of this demonstration. But if you did want to make use of another solver, you could certainly do that. And the other thing that I'm going to be sure of when I look at this dialog box is that I have the Create Idealized Part checkbox checked. Now, it is possible, actually, to go straight from the part file to the FEM file by unchecking this checkbox. But as I described in one of the earlier slides, it's very useful to have this idealized part to create a higher level of abstraction that separates the geometry idealization process from the underlying part file itself. Now that I have my settings in place, I'll click OK, and NX will create a new FEM and simulation for me. And up comes a few options I can set for the solver. I'll get back to that in just a few minutes. But now at this point, I was just told there might be a little bit of a technical difficulty here. I apologize. Give me just 1 minute and I'll see if I can make sure that everyone's seeing my screen here. I apologize for the technical difficulties, everyone, but I think we're back in business. I'm going to back up to the beginning of this demonstration that I recorded and start from square one just so we're all on the same page. So what we're looking at here is 1/2 of a plastic enclosure for a piece of electronics hardware. And so what I want to do is analyze the stresses in this part due to the loads created by the snap fit of the mating half of this electronics enclosure. So what I'm doing is switching to the Advanced Simulation module of NX, and from there I click New FEM and Simulation. When I do that, I get a dialog box with a few options and I'll describe a few of them here. The first thing I want to make sure of is that I have this checkbox checked that says Create Idealized Part. Now it turns out if this is unchecked, it is actually possible to create a FEM directly from the part file. But as I described a few slides ago, it's very useful to have this extra layer of abstraction between the FEM and the underlying part file. So I'm going to make sure that this checkbox is checked. And the other thing I do is double check to make sure that the solver is set to NX Nastran, which is what I'll use for this demonstration. If you wanted to use another solver, you could certainly do that, but for the sake of this demonstration, I'll use NX Nastran. And so now that I've gone through those options, I'm here inside the FEM file now. And so at this point, I'll click the 3D tetrahedral mesh button, and I'll be presented with a dialog box that will enable me to create a tetrahedral mesh on this part. Now what you'll notice is there's a little lightning bolt button here that will infer an appropriate mesh size for this part. And I'm going to dial that down just a little bit from the recommendation. And I'm going to keep all the other defaults. Now the other thing I'll do here is I'll click the preview button, which presents you with this very lightweight preview of what the mesh density will look like. It doesn't fill your screen with more nodes than you can count. It just shows these little clear circles on the edges of faces just to give you a feel for what the mesh density will be like when you accept the mesh with these settings. So as I look at this density, it looks pretty good to me, so I'll click OK and accept this level of mesh density. And it takes just a second, and now I have a 3D tetrahedral mesh on this part. Now the next thing I want to do is assign some physical properties to this mesh. Now you may or may not know that NX actually ships with a rather large library of materials that are available to you. So if we look at this dialog box, you see several of the standard grades of aluminum, several of the standard grades of stainless steel. There's many other materials that you might encounter or find useful as well, including the one I'm going to use for this demonstration, which is a plastic polycarbonate material. And just to give you an idea of what properties actually ship with this library, I can interrogate the material and find out that I've got a mass density, standard mechanical properties such as the Young's modulus, Poisson's ratio, and even some other properties such as the yield strength and thermal properties as well. So as I look at this yield strength value, it's 62 megapascals. So that gives me an upper limit or a ceiling on the stresses that I'm going to look for once I put my simulation together. So I'm going to accept the polycarbonate material. And now it's been applied to the mesh that I created. And now at this point what I want to do is create my boundary conditions. So I'll create fixed constraints directly on the geometry, and because the mesh is associative with the geometry, the boundary conditions will actually be applied to the nodes and elements. So I'm going to fix those surfaces that we just saw on those bosses, and I'm going to apply a 15-pound force load on those recessed surfaces down at the bottom portion of this enclosure. So now I've got loads and I've got constraints. And again, even though they've been applied to the geometry, because the mesh is also on the geometry, the boundary conditions are also on the mesh. So I click Solve, and I accept all the default settings, and now I've got some results. So I'm going to look at the stress results now, and bring this back into view, and it looks like the units are in English, so I'm just going to convert that real quick to metric units. Now I see my peak stress is on the order of 124 megapascals, so that's about double what I'm looking for. Remember, when we looked at the yield stress of the material, it was about 62 megapascals. And we can see, based on the hotspots in the contour, that it's concentrated right at the bases of these bosses. So whatever design modifications we make should be something that mitigates the stresses at the base of these bosses. So what we're going to do is try to find a way to stiffen this bracket and mitigate the bending that we're undoubtedly getting right at the base of these bosses. And so what you'll see now is I'm going to return back to the simulation file. And actually I'm going to go back down to the idealized part now. And now I'm going to promote the body so that I can actually make some modifications to the part file. And at this point, what I'll do is leverage these very powerful synchronous modeling commands and try and make some design modifications. And in the process, I'll actually make several design modifications. Not only will I try to stiffen this, I'll also try to incorporate some changes that I got from the designer and show you how very rapid and fluid this all can be because it's in this very tightly coupled, integrated environment. So the first thing I want to do is actually I want to increase the volume of these holes here to allow for more airflow to cool the electronics inside. So to do that, I'll use the resize face synchronous modeling command. And what you'll notice is by clicking just this one surface on this one hole, the resize face command was intelligent enough to understand that what I really want is probably these other three surfaces as well. And not only that, it's smart enough to impose this equal radius constraint so that whatever change I make to the radius of this circle, the same radius change will be applied to these other three circles as well. And so when I change the diameter in this text box from the nominal value to something slightly greater, let's say 1.26 inches, and I click OK, and then just like that, I've increased the diameter of those holes or increased the diameter of that circle and thereby increased the airflow through those holes. Now the next thing I want to do is try and stiffen up this bracket or this housing to try to mitigate those high stresses we saw. So to do this, I'll use the copy face synchronous modeling command, and I'll select these boss faces. And again, by clicking just that one face, the synchronous modeling command was intelligent enough to infer that I probably wanted all of these other faces as well, and in addition, the mirror image of the boss as well. So now I've got those surfaces selected. I'm going to set a translation vector here, and I want to move it in the positive y direction, so bring it down towards those air holes. And I'm going to set a translation distance here by which to copy these new surfaces. So I'll move things about 2 inches, and I'll click OK. And at this point, I've copied and pasted these faces into place. So now I've got a new set of solid geometry here that's been united with the original solid geometry. So now I have a contiguous volume with just a few button clicks. And in my mind, this is a very powerful feature because you see how complex these bosses are. It's a tapered diameter as you move up. There's some interesting curvature to this connecting member here. And as the analyst, I don't need to know anything about how this design was originally modeled or exactly what extrude operations may have been performed to create these bosses. With the power of the synchronous modeling commands, I can just select these faces, copy them, and paste them into place wherever I want them to be. So at that point, I've made my design modifications. I'll go back up to the level of the FEM. You'll notice we see these very faint black outlines here, which sort of represents this ghosted volume where NX knows the geometry has been updated, but the FEM has not been. And we can also ascertain that by observing the update button here at the top left. So I'll click this button and tell NX to update the FEM that I created with the existing settings. And now the mesh has been updated to accommodate the increased airflow in this hole, as well as to accommodate these new bosses that I copied and pasted down towards the lower portion of this enclosure. So what I'll do now is I'll create a copy of that simulation that I ran previously, because I want to keep that simulation in place so that I can refer back to the results later. And I'll call this solution with second boss. And because I copied that solution, my boundary conditions are still in place. I've got constraints and loads, but the other thing I want to do is add to that constraint set by fixing the same surfaces on the second set of bosses. So I'll do that, leave the loads in place, and tell NX to solve the model. Now that I've done that, I can look at these results now. So let's take a look at the stresses. And again, I'll convert from English to metric. And we'll set this to MPa. So now our peak stress is only 21 megapascals. So we've come down quite a ways from where we were originally. And in fact, we don't see much in the way of stress concentration at all at the bases of these original bosses. Still stress concentrations to some degree around these other sharp edges, but I think that's to be expected. But now suppose I go back and show this concept to the designer and say, hey, I came up with a design that works. The stresses are within the allowable. Does this work? And suppose the designer says, well, it's great that the stresses are now within the yield limits, but it doesn't really work to have those bosses there. We need to come up with another concept. So I'm going to go back down to the Idealized part file and leverage the synchronous modeling commands to rapidly iterate on a design concept until I get something that's amenable from the designer's perspective. So what I'll do now is I'll come in here and I'll delete that second set of bosses that I created, because the designer said that it doesn't really work to have those where they are. So what I'll do now is I'll take this rib that goes across the middle of this airflow hole, and I'll try and raise that up just a little bit to add some more bending stiffness to this enclosure. So I'll select that face, pick some appropriate pivot points, pick the appropriate direction in which to pull the face, and I'll actually set that distance manually. And so I'll pull that up by 0.15 inches. Now that I've done that, again, I'll go back to my simulation file now. There's one other thing I'll do here. Actually, I'm going to take these bosses and copy them down to that rib that I just pulled up, because I do still want that second set of bosses. I just don't want them quite as close to the bottom of the enclosure as I had them in that first design concept. So again, I'll use the copy face command, copy them down the appropriate distance, and they'll be copied and pasted into place automatically. And just to make things look a little bit more nice and neat here, I'm going to delete these little tabs that stick up just so that the surfaces are a little bit more streamlined. So I use the delete face synchronous modeling command to do that. And you'll notice just by clicking the one face on each of those two little tabs, I delete the whole thing, and it doesn't in any way interfere or corrupt the underlying geometry itself. It just deleted those tabs that stick out above the rib. So now I'm back in the FEM file. I'll update the mesh, and now I have a new set of nodes and elements. I'll return to the simulation file, and I'll create another copy of this solution. And again, my loads are in place. Those are still the same. The other thing I need to do is update my constraints. And I'll change the name as well here to give this a meaningful name. I'll call it solution with boss on rib, or boss on tab rather. And like I said, I'm going to update these constraints and fix the inner surface and top surface of these new ribs, or new bosses, excuse me. And then I'll click Solve, and just like that, I'll have a new set of results to investigate. Now I can bring these results to the post-processor. I can create several different layouts and view all these results simultaneously. And if I jump ahead just a little bit here, so now I can see all the stress results simultaneously. And this third result, the stresses are a little bit higher than what we saw in the second or the first design concept, but still within the yield limits. And so at this point, I can go to the designer and say, I found a mitigation strategy that works within your design constraints, and then we can move on to the next task. So what I hope this demonstration illustrates to you is just the power of a tightly integrated CAE environment where you can make geometry idealizations and abstractions and very quickly propagate those changes up to the level of your finite element model and even your simulation file, carry over loads and constraints from geometry that hasn't changed, and rapidly iterate through a trade study like this. So now, having said that, we'll move on to the next set of demonstrations where we'll highlight some tips and tricks. Now, I want to point out here that these tips and tricks came from a presentation that ATA gave at the Siemens PLM Connection Conference earlier this year. We have many more details and much more information for you if you're interested at the link you see at the bottom of the slide. But what we're going to show you today are three of our favorites from that presentation. So in particular, we'll look at the mesh morphing operation, and in the process, we'll see the node association command. The second tip we'll share with you has to do with the advanced NX Nastran solver options. And the third tip addresses post-processing templates. So let's look at the first one, this node association command. From a high level, what we're trying to do here is we're trying to take a non-associative finite element model, and by non-associative we mean a finite element model that has become separated from any underlying CAD model. It's just a standalone collection of nodes and elements. And we want to reunite that with some representative CAD geometry in such a way that the FEM can now be associated to the CAD model, which will allow us to do some very powerful things, namely create loads and constraints on the geometry that will then propagate to the nodes and elements on the geometry. And the other powerful thing we can take advantage of once we've put the FEM back together with the CAD is we can use some of those very powerful synchronous modeling commands to move faces or resize faces and have the mesh automatically update to reflect those changes in the CAD geometry. Now I have another video demonstration here, but I'm going to go to the video here. Okay, I'm running this directly from Windows Media Player, so I hope everyone can see this. So what I'm going to do is I'm going to start by opening a CAD model. Now it could be, perhaps this is the original CAD model that was used to generate the finite element model in the first place, and somewhere along the line the two got separated from one another. Or the scenario could be we lost the CAD model long ago and we reconstructed the CAD geometry by creating surfaces on free element faces and stitching those surfaces back together into a solid body. But whatever the case is, suppose we do have this representative CAD geometry on which we would like to associate nodes and elements. So the next thing I'll do is I'll import an NX Nastran model that represents this bracket. And so I'll just accept these default settings and bring it into NX. And now even though this is all within the same NX window, I really have two files open here. I've got a simulation file or a FEM file with these nodes and elements, and I've got the part file containing that CAD geometry, but the two haven't been tied together. They have not been associated yet. So the first thing I'll do here is I'll just solve this model just so that we have a set of baseline results against which to compare. And just to prove to you that this FEM has no knowledge of that part file, if I expand the FEM node in the tree, you'll notice I see mesh controls, 3D collectors, and fields, but nothing about polygon geometry. So to start the process of putting the two back together, I'll right-click on the FEM in the Simulation Navigator tree, and I'll make it the work part. And now I'll right-click again and I'll come down to this button that says Replace Ideal/Master Part. And then when I click that, it asks me for a part to associate to. And so I'll click that part file that I just loaded in the previous step. Again, I'll tell it to create an idealized part. And now when I click OK, you'll notice a subtle difference. You'll observe there's two slightly different shades of green here. One shade represents the elements, and the other shade represents the polygon geometry. And to prove to you that the two have now been brought back together, if I expand the FEM node in the tree in the Simulation Navigator, now you'll notice we do see a branch for polygon geometry. So the process has begun. So what I'll do at this point is the node association command, which I find in the Nodes and Elements tab in the ribbon. So I'll come down to that button and click Node Association. I'll select the mesh, and I'll select the solid body, and I'll set an association tolerance. And then when I click Apply, the next thing I want to do is investigate the results of this association. I want to find out how many nodes were associated or unassociated through that process. So I can visualize this two ways. I can look at the orphan nodes, or to put that in different terms, I can look at the nodes that were not successfully associated to the solid body, and those show up as these red asterisks. And so really what this means is probably my tolerance was too small. Now the other thing I can look at are the nodes that were successfully associated to the body. And what it'll show me now is a set of blue nodes that are on edges and purple nodes that are on faces. So what I want to do is take another pass at that and try and get these red nodes to associate successfully to the underlying geometry. So I'll go back to the Associate Nodes tab here, and I'll select the mesh, and I'll select the body again, and I'll just turn up this distance tolerance a little bit. I'll change it from 0.1 millimeters to 0.5 millimeters. And I click Apply, and then go back to these checks, and now that I click Show, you'll notice I don't see those red asterisks appearing anymore. So that's my visual confirmation that the nodes have been successfully reassociated to the solid geometry. Now having done that, I can go down to the idealized part and I can start to make some design changes and have them very easily flow up to the level of the FEM. So let's say the designer asks me to make a change and to analyze the effects on the stresses. And so what I need to do here is grab these faces and pull out this bracket to make it longer. So let's say it needs to be 10 millimeters longer. So using the synchronous modeling commands, I can very easily pull that face out and lengthen the bracket. And let's say these through holes also need to be increased in diameter. So I'll bump those up from 4 millimeters to 7 millimeters. So I've made a few design changes. I'm going to go back to the level of the FEM now. And again, we'll see these faint black outlines that represent this ghosted volume where NX knows that the underlying CAD geometry has been updated, but not the FEM. And the other indication of that is if I look at the top left, I see this button that says Enable FEM Update. But instead of doing that, what I want to do is use the Mesh Morphing command. So again, I'll go back to the Nodes and Elements tab, select the Automatic Morph command, and select the mesh. And just like that, the nodes and elements have been stretched and pulled and reshaped to conform to the new design geometry. So the mesh itself wasn't actually regenerated. We just stretched and pulled elements in such a way that we maintain element quality while still conforming to the new design configuration. So now I'll come back up to the level of the sim, and my loads and constraints are still in place. So what I'll do is I'll create a copy of my original simulation so that I can perform a new analysis and compare the stress results against that original baseline design. So I'll create a copy and click Solve here. And just like that, the results are ready for investigation. And so let's look at the first set of results. Let's say we want to look at displacement, for instance, and we see the peak displacement is about 2.2 millimeters, and I'm going to use a second display window here so that I can look at the new set of results side by side. And again, let's look at the displacements. And now we can see the peak displacement is almost 3.3 millimeters. Now this is just a hypothetical example, but you can imagine the scenario where maybe there's some deflection limit on this bracket. Suppose it can't deflect more than 3 millimeters, or whatever the case may be. The point is we're now in a position where we can take nodes and elements, associate them to some representative CAD geometry, and then leverage these very powerful synchronous modeling commands to reshape the mesh and to pull and stretch these elements in such a way that their quality is maintained, but they reflect design changes or design updates that we make, and now we're in a position where we can perform these very rapid trait studies without wrestling with mesh updates or any of those things that happen when you work with finite element models by themselves without any associated CAD geometry. Okay, that concludes that demo, so I'll return to the PowerPoint slides here. Now the second tip we want to share with you today are these advanced solver options in NX. So in the demos we saw, you'll notice when I click the Solve button, we get this dialog box that has a few buttons here that we can click on. So what we're going to do now is talk about two of these in particular, the solver parameters and the advanced solver options. At this point, I would like to point out, we'll dive into these in some detail, but we do have a presentation that dives into much greater detail about memory options and optimizing NX Nastran performance at the link you see at the bottom of the slide. So if that's of interest to you, we encourage you to visit our PLM software website where you can access all these resources for free. Okay, let's look at some things in more detail now. Let's start by talking about this Edit Solver Parameters button. If you're familiar with running the NX Nastran executable directly without doing it through NX, you may be familiar with the dialog box you see at the right side of the screen. And if you are, you'll notice that after you specify the input file, there's also this text field where you can specify optional keywords. So these would be things like memory options or scratch settings, things of those nature. So really what we're doing by clicking Edit Solver Parameters within NX is really the same sort of thing you might otherwise have to type manually in this optional keywords box if you were running the NX Nastran executable directly. So let's look at these solver parameters in more detail now. One of the things you can change is the license type. You can switch from the desktop version to the enterprise version. You can also select the solver executable. There's a bit of a caveat here that you have to look in your NX installation directory for these configuration files and set these environment variables. Now the good news is in NX 10, the default setting is to use the NX Nastran 64L version, which lets you access more than 8 gigabytes of RAM. If you're using a version of NX prior to NX 10, then this was not the default, and so you may need to go in here and manually change these settings if you haven't done so already. But the key takeaway here is if you're not using this Nastran 64L executable, then you can't run jobs with more than 8 gigabytes of RAM. Now there's a few more useful settings here. We can specify the memory. So in this case, I've set 6 gigabytes. But again, if you're using the Nastran 64L executable, you can set more than 8. The other, there's another checkbox here that's labeled old. Now if you check this checkbox, what it does is every time you run an analysis, it appends a suffix with incrementally increasing numbers, starting with 00, then moving on to 01, 02, so on and so forth. If you don't have that checkbox checked, then every time you run an analysis, the previous results are just overwritten. The next setting you can change is this scratch drop-down menu. If you set it to yes, which is what it is by default, it will delete the database files after the solution completes. But you can also set it to no, or you can set it to many. And in both cases, no and many, Nastran will save the database files after the analysis is complete. So if you're in a situation where you want to utilize the restart capability of Nastran, then you definitely want to make sure that this scratch pull-down menu is set to either no or many. Now, on the other hand, if you don't care about restarts, then you can set this to yes and just save yourself some disk space. Another setting you can change here is the scratch directory, or S directory is how it's labeled. And we highly encourage you here to set this to a local solid-state drive if you have access to one. If you do that, your performance will be substantially better than if your scratch directory is a remotely mounted drive or a spinning hard disk. Now, one of the last things you can change here is this parallel text field. So this is where you can enter the number of CPUs you want to use in the analysis process. And lastly, there's a catch-all field labeled additional keywords. So if you wanted to change any of these settings that aren't explicitly exposed, you could do so with this last text box here. And we don't have time to go into what all these additional keywords are in this webinar, but you can look them all up in the Nastran User's Guide. Okay, we've talked about the solver parameters. Now let's talk about the advanced solver options. So when you click this button, you'll be presented with a dialog box that has 3 tabs on it. The first one is labeled General, and what I find useful about this tab is you can set the units. And where this is extremely useful is it's nice to think that everyone works in the same unit system, but oftentimes you get a request from a customer or a colleague and they want your finite element model in a different system of units. And NX makes it very easy to just change this option right before you export the model, transform the model into those units, and then you can pass that on to your colleague or your customer who asked for it. Now, the other thing that can be useful in this advanced solver options dialog box are the export options. By default, it's set to export the full model, but there's a couple other ways you could use this. You could export only the visible elements. So if you had certain elements hidden or shown in your graphical display window, then you could set this to export only the elements that are visible to the graphical display. Or the other thing you could do, the third option here, is if you had groups defined in your finite element model, you could export just a subset of those groups. Now, the other thing that can be useful is in this output options section, and this is where you can export just a subset of the Nastran input file. So by default, all of these boxes are checked, so you'll get a complete Nastran deck that could be run if that was your end goal. But oftentimes, when you're working with a large finite element model, you just want to export a subset of nodes and elements, or you want to export the nodes and elements that correspond to a particular component, and then you want to bundle up a set of include files and put together your input deck manually. And if that's the case, then it can be very advantageous to uncheck these checkboxes at the top here so that all you get is the bulk data. But of course, you can mix and match the checkboxes to export exactly what you want. So we talked about some of these options. Really the takeaway is, especially when you're working with very large models, you don't always want to export the entire finite element model. You want to export just a subset of it or just a few pieces, and there's several different ways you can make that happen. Now, for our third and final demonstration here, I want to show you what post-processing templates are all about. Now, before I show you the demonstration, let me just give you some background and overview here so you understand the utility of these. What templates do is they save all of the view configuration settings and options that you're using in the visualizer to post-process results. So if you change the scale on a color bar, you change the units, you change the deformation scale factor, you can encapsulate those within a template, and then the next time you come back to look at that result set, or the next time you redo a trade study and you want to get back to having that view configuration set up exactly the way you had it before, you can just apply the template to the view, and then with just a one-click operation, you can set all of these disparate post-processing view settings. Let me switch to the video now. So what I'm going to do is I'm going to open a simulation file of a generic spacecraft model, and I've already got some results loaded and saved in here, so I'll bring those up in the post-processor now. And they happen to be modal results, so let's say I want to look at the displacement results for the 7th mode. And now suppose what I want to do is change the deformation scale factor from 10% down to 5%. And the other thing I want to do here is change the range on the color bar from the default to some more meaningful value. And so now that I've done that, now that I've got my settings in place, what I do is I right-click on the post view in this viewports section of the post-processing navigator, and I come down to where it says New Template. And when I click New Template, now you'll notice I have a new entity in this tree down here. So I'm going to rename this and give it a meaningful name. And in this case, I'll call it My Template. And so this template now encapsulates all of these settings and options that I've set in this particular visualizer. And so now to demonstrate the utility of templates, what I'm going to do is return back to the simulation file and close out of all these parts. And what I'm attempting to demonstrate here is if I'm working with the model and post-processing results and I put those away for a few days and come back to look at them later and want to get back to the same set of post-processing options that I had previously, I can use templates to do that. Or if maybe I turn this task over to a colleague and I want to make sure that they are using the same color bar scale that I was using for the sake of consistency, you can use templates to accomplish that. So what I'll do now is I'll open the spacecraft model back up. And again, the results are already in here, so I'll bring those into the post-processor. And when I do so, you'll notice that it's reverted back to giving me the default setting. So the deformation scale factor is back at 10, and the color bar range is now set to this automatic default range. So what I'll do now is I'll come down to the very bottom of the post-processing navigator where I see the template that I previously saved, and I called it My Template. I'll right-click on it and then select Apply, and it will apply that template to the current viewport. And as soon as I do that, you notice now the color bar scale has changed to give me an upper limit of 3, and the deformation scale factor has been decreased from 10% to 5%. So that was a very quick demonstration, but I hope it shows you the utility of using post-processing templates and how they can really facilitate more rapid post-processing so you don't have to waste time and effort getting your options and scale factors and settings configured just right every single time you post-process a model. That concludes the demonstrations we had planned for this webinar, so I just want to recap the tips and tricks we showed you today. The first thing we showed was static analysis of an electronics housing, and we saw this from start to finish. We started with CAD model, we created an idealized part, analyzed it, saw that the stresses were too high, and then went back to the idealized part, leveraged the synchronous modeling commands to update the design, do some trade studies, do some what-if analysis, and finally hone in on a design that was satisfactory from the designer's perspective and the analyst's perspective. We showed you 3 of our best NX CAE tips and tricks. We looked at NX mesh morphing, so you can see how you can take a standalone orphaned finite element model, pair it back up with a CAD model, and leverage these powerful synchronous modeling commands. We looked at the solver export options, and we looked at post-processing templates. And as I said before, we have many more collected tips and tricks. Just to name a few here, matching meshes at an interface, customizing results legend text, and renumbering NX finite element models with the NX Open API. If any of these catch your eye, please feel free to contact us after the webinar. We'd love to field any questions you have or tell you more about these tips and tricks. And that concludes our webinar this morning. Thank you, ladies and gentlemen, for your time and attention. I'll take any questions now if you have any. If not, please feel free to write down my phone number and email address and contact me later if anything occurs to you. And last but not least, I would like to also encourage you to please visit this link at the very bottom of the slide and fill out the survey. We put these webinars together for your benefit, and we want to make sure that you're getting as much value out of them as possible. Thank you very much. All right, I don't hear any questions from people on the line, so I'm going to sign off here. Have a great day, everyone.